Welcome to everyone online, and just for those here in person, if you haven't figured out already, we have our exit through the door in both rooms. The facility is just across the hall, should you need the bathroom, and plenty of refreshments in the other room. I'll hand over to Samuela now.
Yes. Yeah. First of all, hello, everyone. This is Dr. Samuela Guida. I am the IWA Strategic Program and Engagement Manager. I'll share my screen. Let's see if this works. This is my first hybrid event, so let's see. So for the people online, I think you are seeing my screen. The people in person, I'll have the double screen there. So welcome to this Australian end user workshop, Harmful Algal Bloom Early Warning Tools, organized by the PrimeWater project together with Monash University. I'll hand over to Professor Bui, then I'll come back and tell you a bit more about the workshop objective and the structure, and then the introduction part will finish with Neil Sims, who will present the Aqua Watch and it's relevant to his workshop. So without further ado, I'll hand over to Professor Bui.
Samuela, unfortunately, we couldn't come.
Oh,
I have to wear this, or can you hear me?
Yeah, we can.
We can hear me. Yes, so I'm not Professor Bui. So the head of the department, unfortunately, he has a last-minute engagement, so he was here to welcome us. So he asked me to welcome everybody on his behalf. So yes, Professor Bui is our head of department, and he's more than happy to welcome everybody here to Monash University. Our Assam Senior Lecturer of Civil Engineering. I've only joined Monash 2.5 months ago. I'm very, very new to this system. I'd like to first thank Sairo and Tapas for trusting us to host this event here. We really, really appreciate the collaboration we're building with Sairo. I also like to thank, on behalf of Professor Bui, Melbourne Water, Southeast Water, Hunter Water, and Sairo representatives who have made the travel here, coming from Newcastle, it's far away, but also coming from other suburbs to Clayton and not easy. So we all really appreciate you guys coming, and also our special guest Apostolos, who's come all the way from Greece to join us here. We really appreciate Professor Bui and send his thank and acknowledgement for all your efforts. Yeah, and those online who are listening to this from the comfort of their homes, welcome to, virtually welcome to Monash University. It's a beautiful campus. Hopefully we get to host you a future event, including the upcoming cyanobacterial workshop end of September here in Melbourne. We have the acknowledgement of the country. Next slide, please. Yes. So Monash University recognizes that its Australian campuses are located on unceded lands of the people of the Kulin Nation. So that's the Clayton campus, and pays its respect to their elders past and present. For those who are online, for the tradition of the hybrid events, I invite you to acknowledge the Aboriginal land that you're on the Zoom chat. So choose the chat function to acknowledge the Aboriginal land that you're calling from. While you're doing that, Professor Bui also asked me to have a short introduction to our team here. So the team at Civil Engineering includes myself, Drs. Anna Lanton and Brenton Winfrey, who is here today with us, and Dr. Rebecca Henry and Cami, who is my new postdoc. I don't know if it's my luck or her luck that being postdoc with me, but I think it's more my luck than hers. She has to deal with my problems, the new academic and his problem, but I really appreciate Tammy's support for our work. We are the water, wastewater, quality, and treatment and monitoring people. And Rebecca Henry has been done lots of microbiology work, microbiology and chemical QMRI. She couldn't be here, but she's part of our team. Then we have Jeff Walker, who is the remote sensing experts, Val and Tim Peterson, flood, hydrology and hydraulic. Fiona Tang is soil, and then we have our air team, Vic Chan and Jenny Zhang, who are air quality team. So that was what Professor Bui wanted me to pass the message. Welcome you here, have a short introduction to the team, and hopefully we'll have a very nice workshop together. At 2:30, we will go for a guided visit of our labs. You will see a bit what we do for different water and wastewater work. And at 4 o'clock, I sent the link? I think I sent the link of Book the Pub, which is 10 minutes walk, Nothing Hill. So for those who can stay, we can go for a few drinks. What's the choice of drink? My choice will be beer. And probably if the tools you can stay, we can have dinner together. Perfect. So I pass to Samuel again.
Thank you. Thank you so much. Thank you. Okay, so just a little introduction about the agenda today. As you see, we have a really packed agenda full of information. Apostolis Timas from MVIS will, after this introduction and Neil Sim's presentation, will talk about tools for hydroecological hazards, exposure and vulnerability reduction. Evangelos Romas from MVIS will then guide you through some presentations developed in the framework of the PrimeWater project. We'll then have some Q&A. A mini break with the lunch provided for the people in person, and followed by a roundtable discussion and stakeholders' expectation and some closing remarks. These are just a present slide showing you where the presenters of today's sessions are from. As I said, I'm connecting from UK. So just for the people online, but also the people in person, we put together a icebreaker exercise. If you can please join a group map, and I'll try to put the link in the chat as well. Okay, so the map will stay on during the presentation, and we will use this during the roundtable discussion. So you actually don't have to do anything. I'll move you around to the roundtable discussion part when it's time. So I'll go back to the presentation. Today, we intend to initiate discussion on short to medium term water quality forecast and how this translates into early warning services for harmful algal bloom outbreaks. So the main objective of today's workshop are to inform local and regional end user of the PrimeWater tools and the operational forecasting services for inland freshwater, and then reflect on how forecast-based early warning for harmful algal blooms can improve operational risk management. So considering this main objective, I would like to invite you all during the course of today's session to start thinking about what do you think are the opportunities, barriers, risk and benefit, or actually anything else that you think about this topic, so that then during the roundtable, we will analyze this more into details. So just on the back of your mind, start thinking about this so that we are ready for the roundtable. Oops, sorry. Perfect. Now I'll hand over to Neil Sims, Deputy Leader of Aqua Watch, who will talk to you more about Aqua Watch and its relevant to this workshop. Neil, the floor is yours.
Great, thanks so much. Can you all hear me okay? I'll take that as a yes.
Yes, we can online.
Excellent, thank you. I'd like to firstly, on behalf of the CSIRO, welcome you all here and acknowledge the First Nations people of this region, the Wurundjeri people of the Kulin Nation, the Bunurong people and the Wurrung people, and thank them for their custodianship of the lands and the waters that look after us today for tens of thousands of years. Connecting up to Indigenous people is something we've got this really fantastic opportunity to do through the studies of the water that we use. And I'm so excited by the possibility of doing that much more deeply than we are today. What I wanted to talk to you about today, so my name's Neil Sims. I'm theoretically based across the road here in Clayton, but mostly if you Zoom me, I'll be in my dining room most of the time. I am deputy leader of a project called Aqua Watch, which is one of the new missions being run out of CSIRO, one of the very largest projects essentially that CSIRO coordinates these days, drawing expertise from right across CSIRO and also partnering with fantastic people such as PrimeWater, who are joining us here today. I know we've worked with PrimeWater and your and other companies associated with you for many years now, and I wanted to relay the high regard in which the partnership is held, and also the great impression that we get from the work that's been done by your organisation. We're really looking forward to continuing a relationship into the future. Next slide, please. Do I do this? Do you do this? Okay. So AquaWatch Australia, the way we're describing it is as a weather service for water quality. So basically what we want to produce is a system where people can check the quality of their water pretty much wherever they are in Australia and around the world, and also provide a bit of a forecast of likely changes in water quality over the next few days. And of course, that's really why we're here. One of the unique features about AquaWatch, there's a lot of water quality modelling going on around the world. We think that AquaWatch might be the first time that there's sensors connected on and in the water through to satellites in space. We're using CSIRO technology mainly for that, but a lot of our partners as well. And really what we want to do is reduce the impacts from harmful water quality events globally. So we've got national goals really that are around harmonising some of the water quality monitoring systems that occur across Australia. There's a lot of activity there. They're all done slightly differently depending on where you are, and improve the accuracy and delivery of information to some remote parts of Australia. And globally, you know, water quality is one of the key challenges in the world, right? So UN estimates are that there's more than 3 billion people who don't have enough information about the safety of the water that they're using to wash and drink. And in fact, that poor water quality kills more people each year than all forms of violence combined, including war. It's a big deal. So, you know, we're right at the front of this process now and being able to provide improved information to a very significant proportion of the world that really needs what we're providing there. So next slide, please. Excellent. So these are the technology elements really that we are connecting. In the top left here is a thing called hydrospectra, and on the yellow buoy there, that's a hyperspectral camera system that sits above the water. It essentially measures the color of the water and transmits data about every 15 minutes, if you like, or at different frequencies. We have several of these cameras in situ now around Australia and around the world, and they really supplement some of the existing sensor systems that are already existing there. In the middle here, this thing called ADIAS is a data integration and analytics system. It's essentially a cloud data processing, storage and analytics system. All of the data from the hydrospectras will go in through to ADIAS, and that's where the forecasting and other modelling will take place, and the data delivery out to a lot of the end users. There's a smaller box, a smaller sort of circle with a thing called IoT sats in it. Really, that's just saying that the sort of connection between these sensors that we're developing and ADIAS might be variable across the world, and we need to think about how those communication systems work as well. And on the right-hand side, you'll see a circle saying AquaSat. So unfortunately, the Earth observation data sets that are available to us at the moment don't quite meet all of the needs for AquaWatch, particularly in some of these inland areas where we need smaller pixels and high signal to noise ratio for the water and a few other things like that. We're on our way to designing those satellites with a couple of very significant global partners, those sensors. And in fact, there's a precursor satellite, a Pathfinder satellite sensor being built by a team of ours in Adelaide. It's due for launch, in fact, in July this year. It'll just be sort of testing a few of the systems there. So we're well on our way to getting those data sets organised. Next slide, please. one of the key elements and there's an intimate link really between what's happening out of PrimeWater and the forecasting there. And one of our main ambitions in AquaWatch, the forecasting part is the other element of AquaWatch, which we think makes it unique compared to other water quality monitoring systems. That's a really complex thing to do, and I'm really looking forward to finding out more about it today. I'll just quickly add that I actually registered for this workshop without having any idea that CSIRO people were involved. I was just really interested in how this comes together, and then I was kindly invited to give an introduction to AquaWatch by the people I've been working quite closely with for a long time here as well. I should have known, but I'm glad to be here. It's fantastic. So we need to observe a lot of things. There's a lot of data involved in forecasting changes in water quality. Really big task. There's a number of particular use cases that we're working on. Algal blooms is one of the main ones. It's very significant in Australia's water quality sort of landscape, and an important thing globally. It's also something that can be observed fairly easily, or fairly clearly at least, with things like the hydrospectra and from space as well, by changes in colour, chlorophyll concentration, things like that. So very, very pertinent to what we're trying to do in AquaWatch is the very topic that we're talking about today. Next slide, please. So just quickly, we've got our pilot sites already established for AquaWatch. We have about 5 around Australia, depending on how you count them, in various ranges of development or establishment. We have, through TAPIS and some of the other colleagues here, a number of hydrospectra in lakes and coastal areas and estuaries around the country. We also have a number of pilot sites with fantastic partners around the world. AquaWatch is aiming to go global. We want to be able to provide better information to people in all parts of the world. It's a big task, but we're really excited by the challenge. And we've got some really fantastic world-leading partners to work with here. And PrimeWater has certainly been a great partner for us in terms of helping develop our thinking around the forecasting there as well. Next slide, please. So a very rough guide to implementation. The next big date for us really is 2026. And at that time, we want to have a small network of, say, less than 20 sites, I think, connected up with all of those technologies from in situ through to space and into the data analytics platform, operating as an integrated system. And so we've got about, as I said, about 10 pilot sites. We need a few more, and particularly in river systems, things like that. But 2026 is when I think we'll see the actual first connected network. We are getting results coming in from some of our other pilot sites between now and then, of course. After 2026, we start to integrate things like some of our satellite data that we're designing with our partners and grow the number of sites there, really. We'd say 50 to 100. The ambition is, of course, to get many more sites out there. Not all of them will have something like a hydrospectra there, but that's where the EO, the Earth observation technology, can really help us as well. And at the moment, we're in the phase of identifying fantastic partners to work with and reducing the cost of these sensors, making them more reliable, and establishing a community of users for AquaWatch that are going to keep us help improving AquaWatch and keep it operational in perpetuity as well. Once this is established, of course, it becomes a real foundation to leverage a lot of other things off, like ecosystem analysis, biodiversity surveys, that kind of stuff too. Next slide, please. I'm not sure whether that's my last one. I think it is. We're just across the road. We should be talking a lot more about this together. You guys are great partners. Thanks so much for organising this workshop today. I'm really interested to see how it goes. We definitely will be working together. So I'm really looking forward to today, and thank you very much.
I'll hand over to Apostolis, who I think will present with his own slides. So I'll stop sharing, Apostolis, so you can share your slides.
Great, thanks. Thank you so much. First of all, for the opportunity, for being here, for having this great opportunity meeting you all and sharing of 3 years work that we've been doing in PrimeWater. I'm coordinating a team of very ambitious and strong partners working in this EU-funded project the last 3 years, trying to combine satellite data with modeling tools and generate operating forecasting systems, trying to provide insight about how water quality might evolve in advance, having an eye in turbidity, in algae blooms, and other water quality issues, and further down to provide, based on those forecasts, based on this new information, downstream services fitting best possible way water industry's needs and perspectives. So it was a very ambitious, let's say, scope with a strong research component, but also a very strong stakeholders engagement and vision. So today's workshop, we intend to focus mostly on the downstream services, on that component of our project, trying to share our experiences working tightly and in connection with our partners that we're acting as end users, but also beyond the PrimeWater project, how we reached to the point to actually provide a multimodal chain forecasting system that integrates the components I've just mentioned. Hydrological modeling in place, in-lake hydrodynamic modeling, Earth observations that can be used either for monitoring, but also in our purposes for improving the skills of those tools, but also to train machine learning tools to work as predictive instruments for water quality. And at the end of the day, to be in a position to use all this information in actual services that came out of large, let's say, end users requirements exercise that we have performed the last 3 years. So a lot of research took place fulfilling these purposes, and a lot of models, a lot of techniques, can you hear me? A lot of different approaches have been tested, and that was the good thing about it. That was the concept of PrimeWater, testing different ways of reaching the same goal, and try to filter this work based on 2 criteria: credibility, that was part of the scientific work, and then end users' expectations. That leads us to the water quality intelligence suite that actually accommodates the result of this exercise as an operational service. And this is where we will focus today, and hopefully we'll have we will initiate a discussion around that. So this suite actually offers the opportunity to connect fragmented data from different sources, having as a central, let's say, element, Earth observation data that can be extracted, can be generated from satellite imagery. And then, of course, those data can be used for monitoring purposes, but also go beyond that. Used to train models or to improve physics-based models and give us hydroecological forecast, just like weather, as Neil just said. And further down, to use those services, those core forecast services for more downstream applications that we will present in the next few slides. Well, technologically, this is supported by an IT infrastructure that actually manages all those data stream flows, manages a vertical working pipelines, codes, and so on. And of course, visualization components that allows users to have a good and comprehensive understanding of the results of these scientific workflows. Well, I'm using here, well, a buzzword, very, very known to all of us, digital twin buzzword. But this is where these exercise actually lead us to be in a position to digitalize the whole catchment area, trying to be in a position to offer within the catchment level the opportunities to have this forecasted information, starting from weather forecasts, going to hydrological forecasting, river flow forecasting, and then to water quality aspects. And all that enabled and powered by Earth observation data that can be retrieved from satellites. We're going back to the components, the basic components that our concept actually is based on. I'm going through very, very quickly those interfaces. We're going to have, our intention is to have, together with Vangelis Romas from Athens, the next session, a demonstration also of those components live. So I'm not gonna online, so I'm not gonna stick to those slides very, very much. So these are some representations of the visualization outcome of the work and the forecasting models that we're using. So water quality from space, operationally, near real time, acquisition of the satellite imagery, processing, and then delivering to the for use. A lot of attributes can be monitored for water quality. Some of them chlorophyll, turbidity, and other critical water quality parameters. But then going into the predictive components of our systems, transforming weather to forecasts. This is a very important first step towards water quality forecasting, hydrological forecasting, and nutrient fluxes forecasting is a very important aspect of the overall modeling chain to reach downstream to water quality predictions. Again, here opportunities are significant, starting from deterministic to probabilistic approaches. These are strong opportunities provided by our new weather forecasting products that are available nowadays for many organizations, national or international ones. Moving further down, using these hydrological forecasts and nutrients fluxes forecasts, physics-based models can be used, as you can see in the upper part of the slide, to simulate the dynamics of the lake, and therefore to be used further as predictive tools, giving information of the evolution of the state of critical environmental parameters within the lake over time and space. But also machine learning algorithms have been tested in PrimeWater in many ways, trying to understand, but also prove whether they can be used as predictive tools in our cases. Finally, I think this is the most interesting part that came out of the PrimeWater project was, and our discussions with the stakeholders and possible users, was the possibilities of actually repurposing this information, stepping on top of these basic forecasts and creating new ways of taking decisions in everyday operations. So that was a very interesting part of our PrimeWater exercise. It led us to 3 or 4 very specific, very clear downstream services, opportunities that can demonstrate the strength that those new information, can bring into decision making. So early warning systems, systems that can be used for optimizing processes within the water treatment plant operators, but also in reservoir management, more complicated, more complex services for optimizing water transfers among catchments or reservoirs have been tested, have been developed together with with users, and we would like to share our experiences with you in the next presentations. So those were the case studies, the demonstration cases where we worked both for the scientific exercises that we have run, but also for the operational services. So we will borrow from those case studies some of the results that we have produced for today's workshop. So by that, I think I conclude this introductory presentation, and we can move to the next session, which is mostly about having an eye in particular in each one of these 3 case studies. And together with the help from Vangelis, we will have a joint, let's say, presentation, a few slides on my side, and an online demo from Vangelis trying to actually give or describe the best possible way how these services might look as an end result. Okay, so let me switch to second presentation. I'll give it a start, and then Vangelis will take over to continue. Is that okay? From Lake Hume. So in Australia, one of the demo cases was Lake Hume. Well, it's you know better than me and us about Lake Hume, a multi-purpose dam experiencing significant water quality outbreaks. So it's an important water body with particular interest and significant costs associated with those water quality problems. So when we started thinking about Lake Hume, an early warning system was the first thing. 4 HABs were the first thing that came across. I mean, we decided to see how we can actually improve decision making in that field. So there is obviously an early warning system in place right now for Lake Hume, and it's based on nowcast information, as we call it. So grab samples, lab analyses, monthly, more or less, time resolution of this information, and then, of course, 3 or 4 points across the lake. This information is available, is analyzed, and then bio-volume concentration and HAB cells concentration are used as indicators, as proxy indicators for HABs. They're evaluated against the national thresholds for algae blooms, and then warnings are issued. This is the case today, and it works. But we thought, okay, can we somehow improve that? I mean, is there a room there for a forecasting-based early warning system? Either this can be can provide, let's say, deterministic information about the dynamics of water quality changes in the lake. That means magnitude, when and where this might occur. So that's the new things, the new information that a forecasting-based early warning can bring into the table, or even probabilistic service. They can also give us an extra information, an extra piece of information, the probability of occurring something. That would be great. But of course, then, can we consider, I mean, can we forecast biovolume concentrations or cell counts? Well, in theory, yes. Practically, it's very difficult, and we're missing a lot of information there that we can use to calibrate models or to train models. So we have to compromise somehow to find other proxy indicators that can do the work. So obviously that's that could be chlorophyll or other parameters. So there is a compromise. We have to compromise there in terms of having new information, but with other substitutes in decision making. And that is something to consider, of course. And also, this is something that makes clear that this type of systems should be considered as a complementary service to existing practices and not be considered as a competitive new application towards existing workflows. So it's a new piece of information for enabling decision-making and not substituting existing ways of working. Even go beyond that stage, impact-based early warning. Should we base warnings against impact instead of thresholds? Obviously, thresholds, they do intrinsically have the risk inside and the impact inside, particularly when we're talking about public health issues. But can we, I mean, is the impact the same across all sectors that are influenced by water quality? No. Even within the same sector, water treatment plants, for example, do not have the same vulnerability to the same problems. So impact becomes a very important factor in all decision-making when it comes to early warning. So especially in a multi-hazard world, this is of increasing interest. And that was why in PrimeWater we had so much interest in trying to describe the best possible way. What is the impact of these new systems? What is the value of the information that a forecasting system based on Earth observations and modeling tools can convey? And that's, I think, the interesting part for us. That was a very interesting journey. And that's also a big part of the presentations that will follow, how we approach this issue and what were the outcomes of this exercise. So impact has a perspective. So we took this, we try to be in the shoes of different users, stakeholders. So we approached impact in different types. Lake management perspective, obviously this is a very important perspective, since being proactive in a lake level, at the lake level, can really be the most cost-efficient way of tackling these issues. This can easily be seen by the costs involved. For example, when water supply can be a problem due to water quality to the citizens, the communities. Of course, there is a disaster risk management perspective where the impact, where the benefit is triggering anticipatory action as soon as possible. And of course, there are the sectoral perspectives. Downstream sectors that they do have their own internal way of extracting impact for those kind of services, mostly in relation to the optimization of their operations. So different perspectives, we try to investigate some of them. And I think it'll be better off to stop here, to pause here, and just pass the floor to Vangelis, just to start demonstrating how these tools work online right now. Starting from, we had this, we planned to pick up some, for each of the case that we will present, some key, let's say, components, some key features that we will be presented and demonstrated. So for the Harsha, the system supports right now, for the Hume Lake, sorry, the system supports right now the monitoring component with Earth observation data, the hydrological forecasting, and water quality forecasting based on machine learning algorithms. I'll stop here and I'll just switch to Vageli to just give us a quick demo on how these look like in our domain. Vageli, the floor is yours.
Thanks, Apostolis. Good morning, everybody. So this is the platform, the operational platform of PrimeWater. We have 5 case studies, 2 of them in Australia, 2 of them in Europe, in Sardinia, Italy, and 1 in United States. Each case study has its own customized services. I will start with the EO monitoring functionality, which is present in all case studies. And since most of you are in Melbourne, I will start with Melbourne's Western Water Treatment Plant. And this is the Earth observation functionality. We are able to produce EO-based water quality products from Sentinel-2 and Landsat 7 and 8 missions. These images are processed with special algorithms. What you see right now is processed with EOMAP's MIP algorithms. Also, other project partners like CSIRO and NASA have used their own algorithms and produced images for oral case studies that have been used in the scientific experiments. But currently, what you're showing, what you're looking at in the platform are processed with the MIP algorithm. So right now we are looking chlorophyll values. We have populated the platform with imagery from 2015 to 2022. This is the latest image available for chlorophyll. By clicking on any point on the map, you can read the chlorophyll lay values. And we can also go back in time and browse the images. Where you see little gaps, these are probably due to, most of the time, due to cloud cover, as you can see in the true color image. And this is a very demanding, the Melbourne Water is treatment plant. It's a very demanding case studies for EO because due to the small size of the ponds and these narrow strips of land that interfere with the water and distort the EO signal. So we are able to produce imagery for this case study only with Sentinel mission at resolution 10 by 10 meter. Landsat has a larger resolution of 30 by 30 meters, so we're not able to provide information for this case study with Landsat. And the parameters that we're able to quantify are chlorophyll, turbidity in NDU units, total suspended matter, total absorption, Secchi disk depth, and also a harmful algae bloom indicator. This is based on the presence of phycocyanin and phycoerythrin pigments and quantifies the probability of presence of cyanobacteria. I'm going back to the second case study in Australia in Lake Hume, again in the Earth observation. Here we can also have information about Landsat 8 at a resolution of 30 by 30, and the Landsat is able to provide also surface temperature since it has a thermal sensor. And another useful, let's say, functionality in the platform is here we can view historical values for the past period in any given point. For example, here is the historical time series of chlorophyll at any point we might select. So this is the EO monitoring application. It is used for monitoring, but as Apostolis said, this is also used for training machine learning models and calibrating and improving the skill of physics-based models, as I will show you later. Now jumping from the monitoring to the forecasting services, I would like to present you the hydrological forecasting model that we have deployed in Lake Hume. This model is run by SMHI, and it uses ECMWF's meteorological forecast and is able to provide river discharges and nutrient influxes at our reservoir. At the map right now, we're seeing all the upstream catchments of Lake Hume. Those two catchments are directly entering the reservoir. So by clicking on any one of these, we can see right here the outflow from this catchment that enters the Lake Hume. Here is the forecast for today's river discharge. It's still early morning in Europe, so today it's 19th of April. These values might get getting updated as we speak. So for today and the next 10 days, we can have estimations of river outflows, water temperature, and also nutrient fluxes like nitrogen, phosphorus, and suspended sediment, which are a very valuable input for the water quality model inside the reservoirs. The hydrological models is offered in both in deterministic and probabilistic, let's say, modes. Currently, we're looking at the deterministic mode, so a single forecast for each day. I can also switch to the probabilistic, let's say, model. So here we have produced an ensemble of model prediction. So for each day, we have an ensemble of 51 equal, probably, let's say, model answers regarding the forecasted parameters. So you can see here for the next days again the different members, the prediction of river flows from the different members. And so apart from the, let's say, the median value of the model, we can have some statistics, some percentiles about what is the expected range of values in our catchment. And this is a very nice way to quantify, let's say, uncertainty in a way. There is another setup, another hydrological setup, which is available only in Europe, which is in seasonal mode. So there, instead of 10 days predictions, we are able to have a seasonal forecast for river discharges and temperature for up to 7 months, aggregated in weekly values. So this is the hydrological forecasting, which is a valuable input for reservoir management, because we can have estimations of river inflows and nutrient fluxes, and also valuable input for the water quality models that I'm going to show you right after. So since we are now already in the platform, I will jump to another case study, which is in Lake Harsa in the United States, in Ohio. And the Lake Harsa is a reservoir where it's used for potable water abstraction and for recreational uses. And here we are moving further down. Sorry. We are moving further down in the modeling, let's say, chain, and we have developed some water quality models, both physics-based, both three-dimensional models and machine learning models. I will now start with the machine learning water quality models. So we have used the EO-based water quality products from Sentinel and Landsat to train some machine learning models. So these machine learning models are using as input meteorological forecast and the hydrological forecast I've just shown you, and they are able to predict, let's say, forecast of chlorophyll concentration for up to 10 days. In Lake Harsa, we had also a very rich data set of in situ measurements, and so we have also trained a machine learning model based on in situ analysis. We have used various techniques, various families of machine learning methods. One very common technique is random forest. Is an ensemble-based, let's say, technique, and we have trained these models into different areas inside the reservoir. And by clicking on the map on each one of these points, we can see the model predictions, the chlorophyll A concentration for today and for the next 10 days. So we have trained these models in two different parts of the lake because the lake shows different patterns in the west and the eastern part. Another family of machine learning algorithms is based on Gaussian process regression. This is a more black box approach. Let's say it's not so easy to understand the effect between the driving forces and the results, like in the like in the random forest technique. But one good point about Gaussian process regression is that they can give us an estimate, a confidence interval. So apart from the prediction, the central value of the prediction, we can have estimations of the 18th and 19th percentile. So again, this is a very nice way to let's say to quantify the uncertainty of further forecast. And I would now like to jump to a third method. So this is another way, another technique to produce, to give information about water quality. This method is random undersampling boosting, and we have trained this model with in situ cyanobacteria cell counts. But this time, instead of quantifying, let's say, the cyanobacteria cell counts themselves, we have opted for quantifying. We have treated the problem as a classification problem, and what the model predicts is the probability that we are above or below a critical threshold, and this threshold is 100,000 cell counts per ml, the limit set by World Health Organization. So for each day, we have the probability that there will be this threshold will be exceeded or not. Again, this is an ensemble technique, so we have trained a large number of models. And when the majority of the models says that this threshold will be exceeded, then we are pretty sure that this is going to happen. But there are also times that half members might say that the threshold will be exceeded. The other half will say that the threshold will not be exceeded. So in these cases, we might not be able to issue some forecast, and we are in an unresolved, let's say, state of our model. So with machine learning, we're able to train models to specific points. These points represent the surface, the top surface of the water body, because they have been trained with Earth observation, and Earth observation represent the top layers of the reservoirs. And we have also later in another case study, in the Europe's case study, I will show also which additional parameters we can, let's say, quantify and forecast with physics-based models. But now, since we are still in Lake Harsa, I would like to show you, demonstrate you the early warning functionality. So the early warning is actually takes the forecasted information from the water quality models and interpret this into warnings customized to the downstream end user. It's like actually the early warning is a first screen that an end user might want to see, to have an overview of its reservoir, like a dashboard. where he can very quickly look if everything is okay with his reservoir. This is the early warning application for Lake Harsa. In Lake Harsa, we have identified, let's say, with the end user, 3 specific areas of interest. This is the potable water abstraction. Another one area of interest is this part of the lake, which is used for swimming and recreational activities. This is another point where the water is, let's say, discharged to the downstream river. And with this, let's say, square area, this is an auto-generated area. It moves from day to day, and it identifies the part of the lake where the highest, let's say, chlorophyll A concentration appear for the next few days. So for each area of interest, we have some graphs. Here we have the relevant graph for chlorophyll A variation. For the other 3 points, we have also some included some indicators useful to the downstream users. For example, here is a phytoplankton production indicator. For every day, we classify the production, the chlorophyll values inside the reservoir according to the WHO limits, the threshold of 12 and 24 micrograms per liter. So currently, you see that we are in the moderate, let's say, state. Our chlorophyll are between 12 and 24 micrograms per liter. We have also a phytoplankton intensification index. We can, as we also can see in the graph, there is an increase in the chlorophyll values in the first day. So this indicator warns us that there is a significant decrease in chlorophyll values, while for the Thursday and the Friday's forecast, this change is not so significant. And here also in the recreation area, we have also another indicator about the suitability of bathing water for recreational activities. So actually, this indicator is expressed as a percent, and the 0% suggests that that there is no part of this, let's say, swimming area that the chlorophyll threshold exceeds the 12 micrograms per liter. But as you can see in the tomorrow's forecast, this index has jumped to 100%, which means that all of the area here is the chlorophyll A concentration in this area has exceeded the 12 micrograms per liter. And actually, if I overlay here the forecasted chlorophyll values, we can see that we are starting today with chlorophyll values. The green color, it's around 11 micrograms per liter. But as I move, let's say, this timeline forward to the future, the chlorophyll A values increase and are exceeding the limit of 12 micrograms per liter. So this is an example that we have a warning issued for this, let's say, area. So the water manager, the operators might be prepared, might want to make some extra sample analysis, or might want to inform public, or even close down the beach to avoid any potential health issues. And I think this is a good point to jump back to our to Apostolis and to show you the presentation about this early warning system that we have developed in Lake Harsa.
Thank you, Vangelis, for this demo. I think it was a nice opportunity for all of us to have an inkling about the opportunities. I mean, how we managed to streamline this information that is produced towards a more manageable, more digested information ready to be used for decision making. And just to say that these visualizations that we have included in PrimeWater is to a large extent is based on the expectations and the need and the requirements of our partners that are at the same time end users in their operations. Has been customized for that. So we have little time left, and I think the most interesting part is the demos. I'll just go through very quickly through that presentation, because I wanted just to depict how we approach the value model in our case. Because science is great, we can provide a lot of nice new information, but does this convey a value? And that was the big question that we tried to work on. So that was a challenge in Harsh, as described by Vangelis, in a lake that is impacted by HABs almost every year, the last 10 years. So there is a recreational activity there. So that was the perspective in this case, the recreational activity, and how we can improve that type of operation. So from the perspective of a recreation manager, or well, in some cases, the reservoir management might be also the recreation management, or depends. So here, for example, as in Australia, there is a certain decision-making process regulated by certain guidelines issued and so on. Here, for example, issue warnings is based not on cell counts or biovolume concentrations, but to cyanotoxin concentrations. Again, here, the decision is based on sampling, lab analyses, and so on. So what was the challenge, and what was what we had investigated? I mean, can we have an influence in visitors' exposure window? So that was the big question. I mean, visitors that go in this place for recreational purposes might be come in contact with toxins. And there is a certain, let's say, exposure window that has been estimated together with our partners there, the EPA. And the big question is how a forecasted based system can improve that. And this is where we can actually extract value. So again, that was a description of the systems that have been tested and demonstrated by Vangelis. So that was the questions that we tried to answer in order to quantify the value, in order to try to figure out what is the actual real impact that the system might have. So if it can trigger any action, because if we cannot do anything about this information, then, I mean, it's nice, it's good to have it, but can we actually do something with that? So by being in a position to change something in our everyday operations, this might be the case that can bring the additional value. Of course, what is the impact? I mean, okay, we do something, but does this has an impact? I mean, how large is the impact that we have? Of course, what are the alternatives, the other options that we can compare? I mean, is it worthwhile investing towards this direction? If there's another way of doing the same thing and it's more economical or more efficient, why doing this one, not taking the other one? And of course, a nice concept that we try to investigate is how certainty of our systems might influence the actual value. So all those questions, I'm going through very quickly that. I mean, those slides will be available, so I don't want to consume time for presenting, but rather demonstrating. So we tried to have a clear boundary for this analysis. So we're talking about short-term benefits. So we're not looking at long-term, let's say, impacts of HAB, for example. So property value losses and so on, they take a long time. So they're not associated with a short-term forecasting system and an early warning. So we're just rule them out. We just consider public health issues and costs in this cost model that I'm going to describe. So that's some assumptions that we've elaborated for the value model. The costs incurred per person when they're actually are infected or by some toxins, some assumptions about the visitors and the percentage of those visitors that can be exposed. Again, we had a mixed approach here, talking with EPA, but also with relying to literature on these issues. And then, of course, costs for the campaign and some costs, some economic cost or benefit from the activity that visitors actually can generate in the recreation industry. So we assumed that $100 per day per person is a fairly reasonable amount. So that was the assumptions. Again, let's take those as assumptions. It can be this way or another way, but let's work. This is our working scenario. So again, what about the alternatives? We went through what are the possibilities there. I mean, obviously, somebody can do monitoring, regular monitoring campaigns. This is mostly usually the case. But this, well, what we call naive monitoring, it's not naive at all, but it's something that somebody does regularly without considering other parameters like historical, let's say, probability of having these events. So this practice can lead to up to 7 days exposure window. What does this mean? Well, there's an assumption again behind that says that even if you're not predict or if you're not issue a warning, people will tell you. People will tell you within the next 5 days. So that's something that's a rule of thumb that usually comes from the practice. But in the States, in this area in Ohio, that seems to be the case. So 5 days is considered adequate time for citizens to report back, even if you are not in a position to actually issue warning later. So we have 5 days for that. And there's another 2 days that it's considered as a minimum unavoidable time for exposure, because you need some time to run the bureaucracy, the issues. To issue the warning, you need to do the processes. You need you need time for that. Even if you measure your HAB there, you need time to issue warning. So that's approximately 2 days. So even if you have a HAB, even if you measure every month, well, what we consider in our analysis that only up to 7 days you will have an exposure window, and then you have also costs. But then you can optimize that approach by actually considering historical data and the probability of actually having a HAB. This might lead you to a more optimized monitoring approach, considering all the costs involved. And we run this exercise for Harsha, and it seems that in different months, somebody can use a different monitoring approach. I mean, in terms of frequency, more frequent monitoring campaigns in some cases than others. So there is an optimized way of doing things, even without forecasting. So we considered to actually make a comparison against that and not the naive monitoring way. What actually is the benefit here is that even if you can have a very, very small exposure window with an optimized approach, still you have 3 days. The 2 days, which is the minimum unavoidable, and at least 1 day, because you need to run a test at that point. So forecasting can save this 1 day and go down to the minimum unavoidable window. And the question is, okay, what does this mean? Is 1 day so important? But this is actually where the adding value lies for this additional system. So we've done the maths there, and I'm just presenting some numbers. Well, it's a complicated, let's say, slide, but let's stick to the last number. It shows that this particular day might minimizing the exposure window, even for 1 day, that might have significant benefits for those months that we've been experiencing HAB events. So those are the numbers out of the exercises. Doesn't really matter what are the numbers, but these vary according to the assumptions, according to the area, according to many other things. But it is important to understand that there is a value there, even by by cutting down even 1 day of exposure for the public benefit. The thing is that this is what's happening in the perfect world. When our models are perfect, they're fully certain, 100% certain of what is going on. So what is going on actually when our models are imperfect, which is the case? So we try to introduce this additional parameter into the evaluation. So we evaluated our model's performance against actual historical incidences, how they actually, we test them in the hindcast period that we had for 5 years against their positive true or positive negative skills. So we collected these with those statistics, and then we introduced that to the analysis. As you can probably imagine, this value falls down. Actually, in some months, our system seems to, not to incur any additional value. I mean, if you can see May and September, then the positive numbers become negative, but still there is a value in certain cases. So even in a real world, even considering the uncertainties involved, there is value that can be extracted from these services. And of course, I'd like to stress out here, this value is very much dependent on the local cases, on the local case context, but also on the modeling, because the skill of the model is very, very important. And also the skill of the model and where it operates well. I mean, whether it also gives a lot of false positive or false negative information is important, particularly when this is penalized, as we did it here by losing $100 per person per day if somebody closes, let's say, the beach without any reason. So it really depends on the model. It really depends on the case study, but yet it seems that there is a value there that can be extracted. So I'm just, that's a summary of these results. I think we're running out of time, and we have another case study to plan to present. I would like to skip the presentation. I've actually prepared for that. It was for a Mulagia case study. In Mulagia case study, we have a more, let's say, comprehensive approach in terms of this platform, because we have included a lot of modeling opportunities there, not to confuse the end user, but to provide him tools to manage the uncertainty. So it's a multi-modeling approach, starting from catchment level, going to the lake level, both in terms of hydrodynamics and water quality, and some very interesting services, which is the blending service. I'll skip the presentation that I have, and I'll try to pass the floor to Vangelis, because I think it's better off to have a demo about this particular end of pipe service that is very, very customized, of course, to the expectations, the needs of owners. So for the next 5 minutes, Vangelis, if you can just, go ahead with the demo for this particular component, and of course, the presentation that I had prepared will be available after the workshop for everybody that wants to have access to it. So how can I just, right. Vangelis, can you hear us?
Yes, and I have also shared my screen.
Right.
Let me know when you're able to see.
I think this is better of Vangelis to have these 5 minutes just to present that. Let me say, as long as Vangelis is preparing the demonstration, that we run a similar exercise of the value of information that such a system provides, a similar exercise. I mean, where is the value about that? I mean, why to use a system that actually to optimize water transfers between interconnected reservoirs? Where is the value? So we actually done that, again, with a perspective, with a narrow perspective, which was focusing on water treatment plant operations. So we used elasticities, water quality elasticity methodologies there to describe the correlation of water quality with the operational costs in water treatment. And those correlations actually gave us, based on the improvement that we can we can have in the water quality give us also an indication of the possible value, but again, in a narrow perspective, which looks very clearly to water treatment plant operations. The good thing, of course, in water management at a lake level is that you can add many of these values that downstream users might have, and therefore to have an advantage operating as upstream as you can do in managing proactively water quality problems. So I'll stop here. Vangeli, please go ahead.
Okay, I have jumped back again to the platform, to the Moulagia case study. This is a preview of the... So this is the three-dimensional water quality model that we have set up for Moulagia case study. This is a coupled hydrodynamic and water quality model done at 100 by 100 square meters. So we are on the hydrodynamic model with forcing from hydrological model and meteorological forecast. The first thing is to resolve the circulation pattern inside the reservoir. So for each one, for the next 5 days, we solve the velocities inside the reservoir. And then we run a water quality model. Here we are able to see chlorophyll A values for the top layer of the reservoir. And additionally, we can have estimation about the nutrient levels, dissolved oxygen and temperature inside the reservoir. As I said, this is a three-dimensional model, so we can have, unlike the satellites and the machine learning models, we can have predictions for deeper layers as well. And actually, some nice tool for examining the vertical profile is this, let's say, the cross-section and the depth variation, let's say, profiles of the lake. So at any given point, we can have estimation of this variation of the selected parameters in all dimensions. So these are a very quick overview of the three-dimensional hydrodynamic and water quality models. I now would like to jump to a special functionality that we have developed for this specific case study. Actually, in the Italian case study, the Moulagia reservoir is used for potable water and for agricultural and industrial purposes. But there is also another upstream reservoir, the Flumendosa reservoir here in the north part of the screen. And the local managers are able to transfer water from this reservoir on demand through a gravity tunnel. Most of the time, the upstream reservoir has a better water quality. And currently, the water managers are doing this blending, let's say, this water transfer based on water quantity criteria. And even when the water quality is taken into consideration, this is done most of the time empirically. So together with ENAS, we have developed these tools. We have developed models in both reservoirs, and we have set up this scenario blending optimization tool. So right now in the screen, you can see that together with the ENAS, the local end user, the local water manager, we have selected 3 areas of interest, 1 in the Flumendosa Dam and 2 in the Moulagia Reservoir. For each one of these points, the end user might set some environmental criteria. For example, here the user have said that for Flumendosa Dam, he wants the maximum chlorophyll concentration for the next 5 days to be less than 10 micrograms per liter. Again, these points and these parameters have been selected by ENAS, the water manager, and as you can see, ENAS has also put let's say have set some thresholds also for the upstream reservoirs, because although he wants to improve the water quality in its main reservoir where water is abstracted from, at the same time he doesn't want to deteriorate the upstream reservoir. So these are the environmental thresholds set by the user, and in this table we can see a series of scenarios. The base scenario is the scenario that no water is transferred between these 2 reservoirs, while scenarios 1, to 10 are scenarios where a small amount of water is transferred from scenario 1 until scenario 10, where a volume close to the capacity of the gravity tunnel is transferred. So right now we can see that even with the base scenario, even without transferring any water from the upstream reservoir, the environmental criteria set by the user are met. But if, for example, I will now set a very strict, let's say, threshold for the Mulagia reservoir, so I want the chlorophyll values not to exceed 5 micrograms per liter for the next 2 days. So this is a strict, let's say, criteria. And now we can see that the base scenario fails to achieve those criteria. So if we don't transfer water from the upstream reservoir, someday in the next 5 days, the chlorophyll will exceed the desired value of 5 micrograms per liter. And what we also can see here is that the first scenario that can achieve those criteria set by the user is the second scenario. So in this scenario, which is about transferring 4 million cubic meters per day from the upstream reservoirs, improves the water quality according to the user needs. And this is the water blending is a very complex problem. It is not always the case that more is better. Sometimes the water in the quality in the upstream reservoir might be worse than the main reservoir. Or there are also cases that we have seen that transferring big amounts of water might disrupt, might affect the hydrodynamic pattern, might, let's say, break the stratification. So this is a very complex problem that could only be resolved with 3D process-based model and not with machine learning models, exactly because it involves also the circulation pattern. And this is a very useful tool that we have developed together with ENAS and.
Vagili, thank you so much. It was a little bit stressful for you to wrap up this very this very condensed demo. It's a very specific application for a very specific problem, but this is a very good indication of how water quality can be introduced in decision making when water transfers is implemented. Obviously, cannot be dictated by water quality. Obviously, water demand and hydropower are dictating mostly the water transfer patterns. But this is how, for example, some agencies would like to introduce water quality in their decision making when they do implement such operations. So by that, I'd like to pause here, to stop here, to make a short break. Is it Q&A now or lunch? Yeah. So I'll pass the floor to Tapas. Thank you so much for attending that, and happy to take any questions. I hope we provided a nice context for the discussion to follow, to stimulate some thoughts and some suggestions. Thank you from our side.
Thanks, Apostolos. There was really a lot of information encapsulated in very little time. So I have a couple of dot points that I have. We have experienced EO benefit, Earth observation benefit for particularly freshwater people who are working in utilities, catchment management, water resource management, river, dam, and so on and so forth. We have also learned how forecast can help improving our decisions. So not much to say from my side. I would love to hear from you. So if you've got any question, we can put that to the right person. So based on the presentation so far we had this morning. One question from me, Apostolos, the tools that you have developed, they're all based on satellite data, and there are specific satellites that you have captured those images from how much ground truthing have you done?
Right. I mean, you cannot actually live without ground truthing. It's really important to validate both. I mean, all those workflows have been validated one way or another. Ground truthing. I mean, Earth observations have been tested against ground truthing. Models have been tested against ground truthing. So we have used ground truthing as a benchmark for the performance of the skill and the skill of those services. So yes, the answer is yes. In situ measurements played a key role, an important role in this exercise.
And I believe we'll do so, particularly for all these models that we are talking about. We need data. More data is good for having a good model. Anyway, any questions from the floor?
Yeah, there was a complex model tool that he showed there last. The customization of what the end user likes. Can you give us some sort of an idea of how long it took to develop to get to that end state view that we saw in that last piece that Evangelos shared? Right.
I mean, visualization is takes long when you're co-developing something, because it's not so clear also for the user of such services how exactly you can use a new tool. So when there is co-development in place, it might take some time, because you're running many agile rounds of discussions and requirements and development and so on. But also, this is just for the visualization part. I think the most intriguing or difficult thing is to provide skillful models to support the visualization. So, and that was most of our concern was there. I mean, how to work with how to be in a position to provide skillful, strong, reliable, credible information out of the models that we're using. So that was a scientific part of our work, to assess different options, to choose those among whatever we tested that fits better this criteria of credibility, that showed up to be a very important decision-making parameter from the point of view of end users in adopting such systems. So in terms of time, downtime. Yeah.
Yes. Well, thank you for this session. And I will also would like to request those online, please use the chat button and put your questions if you have any, and we will pass this on to the speakers and we'll get you an answer. Thank you very much. So, no, so so the lunch is outside. That's right. So please go, and we've got 10 minutes. So 10 minutes break.
10 to 20. I think the break is until 1:30 there. So it's a 15 minutes. Yeah.
So please grab your lunch and come here, and then we start the next session.
For the people
and those
online,
please have a little break, and then I'll see you in 10 minutes time.
Time for the roundtable discussion. Tapas as well, and Neil and Lee. Great, thank you. So we have quite a lot of people online and people here in the room, so we'll try and manage that as good as possible. My name is Arnold Dekker. I'm subcontracted to Saro, and via Saro to PrimeWater. But I also nowadays work part-time for Saro as well on the AquaWatch project. So it's nice and complicated, and I'm on the conflict of interest register, so that's okay. We know about this. Okay, roundtable discussion. We have end user stakeholders online, national ones, international ones, and we have a lot of experts. And I'm going to try and focus on the end user stakeholders initially for the first 15 minutes. Then I'm going to try, then the scientists and the other experts can chime in, and then we'll have a general discussion. That's just a a way to make sure that we capture the end user stakeholders and that they've got an opportunity to respond. Now, if you go to the roundtable discussion on the group map, you already see a very interesting effect, which is that the opportunities and benefits are have got about 5 entries. The barriers now have 10 or something entries, and risks 4 entries. So that is really interesting, and this is valuable information. So I did think of first going to the opportunities and benefits. Let's look at the positives. And there probably are more positives. And I'd like the end users and stakeholders online to unmute themselves and open their videos and then maybe provide more benefits, because we do hope of opportunities and benefits. We hope there are more possible. Anybody online? It's very quiet. How many people do we have online? We have 17 people online. Some of them are here. I know.
We could put avoided costs for additional treatment at treatment plants if that's not already on there. I can add that in.
Avoided costs. Can you repeat that one?
Yeah, so avoided costs if we don't need to implement additional treatment processes at treatment plants, because we can manage the algal blooms in other ways. So if we have some kind of in-reservoir intervention that we can implement more cheaply than, for example, powdered activated carbon dosing or something like that at the treatment plant.
Okay, thank you. Samuela, can you put that in there? Can you summarize that and put it in?
Yes, if you maybe add a couple of words in the chat, I'll then put it in the
So this was Abigail, wasn't it?
Yeah.
Yeah, I can
Yes.
add it straight into the board. That's
If you can add it straight,
Thank you.
thanks. Excellent. Thank you. Any other people online?
Utility representatives here.
Yeah, sorry, Tapas, I was asking that.
Yeah.
Okay, thank you. So the utility people here. So could you please speak into the, I think it's on. Can you try?
Yeah, is it on?
Yes.
So if you're not sending people out into the field, then potentially you're reducing your OH&S risk profile.
Could you repeat, please? We are talking about benefits, correct?
Yes. So this
And
would be a benefit. So could you repeat that benefit?
Maybe I'll just
Yes.
make it easy. I'll second that. Yeah, definitely the OH&S or risk reduction of having people out and over water more often. We can reduce that. And it's definitely something we've identified as a value add. The other definitely that we're tying into is the reduced use of, for example, the vehicles going out there, the boats on the water. It is actually flagging as a carbon footprint reduction type value add as well. Not massive, but it's something that we've flagged that less equipment being used. So other benefits too, it was touched on with the lead time around, if it's an average 7 days turnaround to get from we need to test to validate the result, having that ability to perhaps on demand or every 15 minutes, check in with what's happening. That's definitely something that we see as a benefit for us, and with the health and safety access is if we have bushfires or poor weather, the boat breaks down, all those sorts of things that can happen. We're not saying it will totally replace what we do now, but it's definitely, if we can, we're taking less steps out of the value stream to achieve the same result.
Okay, thank you. That was a great contribution. So I think extreme events is something where these kind of methodologies could play a role, because in extreme events, often in situ sensor networks don't work. A great example are black water events. When you've got floods in Australia and massive amounts of water go across the landscape, you can't measure that with in situ sensors. So you'll have to do it with something else.
We have a question from Glenn online, maybe for Apostolos. How useful is this system likely to be in narrow, sinuous river systems? And what is the maximum reach width for it to be useful?
Right. Okay. Well, in terms of monitoring from remotely narrow water streams, the constraint there is the resolution, the special resolution of the sensors that somebody can use. Nowadays, there are a lot of opportunities and a lot of possibilities, options available, free satellite sensors, but also commercial ones with different spatial resolution capacities, starting from 300 meters to 300 meters, which is not obviously fit this particular purpose. But then Sentinel-2, for example, can go down to 10 meters per 10 meters. So each cell that can actually extract information is of that size. And of course, if somebody goes to commercial services, then the resolution can be much more finer, down to 0.5 or 0.3 per 0.3. But I think Arnold and the other colleagues here in CSIRO are more, they can answer this question much more efficiently. Now, when it comes to modeling, then things are different. And I think that's the benefit of those kind of integrated approaches, because one system can actually fill the gaps of another system. Modeling can be used to fill the gaps in terms of time between consequent images, or even in space when as Vagelis showed us with the 3D dimensional modeling. So I think that's those integrated approaches. I think this is the best, the most strong asset of those approaches is exactly that they complement each other in these attributes. Thank you. I hope I answered, but I don't know, Arnold or John, if you want to add something in terms of remote sensing capabilities.
Yeah, thanks, Apostolos. I think you've answered the question in terms of resolution, in terms of spatial resolution. And I think that there's real opportunity for us to integrate a whole range of different sensing technologies into the models. And I think that by having the EO services be somewhat agnostic is an objective that we are aiming for as part of these operational services. So equally, you could be using high resolution data, but it may not, if it comes from a commercial source, it may not be available on the operational basis that free services like Sentinel and Landsat may be available, but that may be still of use to you in terms of your forecasting services available. The other thing that I was going to mention was there's also services, EO services, hyperspectral services that give you a lot more information from the EO data products rather than just the multispectral data. They're not available in the type of resolution that would be suitable for sinuous river systems at this point, but there will come a point where we can integrate this data into the services as well. And indeed, Apostolos has done this in the project and integrated hyperspectral data from the Prisma sensor.
There's a few people here. Are there any people online who want to speak before I hand the microphone in the room? Because in the room, it's always easier. I don't hear anybody. So who was first? I think.
Yeah, maybe this is a question rather than a comments. I'm curious, maybe a bit of further elaboration to see how this system could contribute to the emergency situation or some incidents management. So why I ask this is because we have discussed about the lead time and the laboratory test. What happened is last year, I think end of the last year, in north of Victoria in Melbourne, there's an industry legally discharged some nutrients, large amount of basically wastewater with a lot of nutrients, and to a river, and which caused a lot of dead fish and even dead cow in the river. And so this triggered some EPA's action on that. So I'm just curious because potentially the time is potentially relatively short rather than like 7 or 10 days. So not sure if this system is able to do something or contribute to the incident management or some emergency situation.
Just some other things that have been discussed, not really in the plan for this trial that we're doing, but one of the things down the track see some value in is potentially the general public can have access to live data of the water. If we are bringing those rivers and recreation areas back online, there may be, we jump on the weather app to have a look at the radar and things like that. And there could be something there for public access for water quality type.
So that's an opportunity.
Yep. So
would you put that under opportunities?
Yeah, okay. To turn that into a benefit though would be, yeah.
Well, yeah, opportunities will become a benefit.
Yeah.
The benefits, I think, is about what we've shown now. And then the opportunities are, what could we think of in the future to add?
Okay.
Let's think of it that way.
So we're starting to measure things that we weren't before in more the spatial resolution. For example, our Grahamstown Dam is 28 square kilometres, currently monitoring that from 3 discrete points. So it's great to have that. Yeah, so, and I'll leave the other for the opportunity one. Thanks for pulling me up.
Yeah, no, it's okay. Nick?
Sorry, I'm going to go a little left field here, and perhaps I'll be not liked for this comment, but so this is being sold as the weather service for water quality. I'm personally quite skeptical that future will eventuate anytime soon, and quite skeptical that CSIRO would be the entity to deliver that, given the liability aspect that will attend such a service. I mean, to start with, what is massive now in the water industry is cybersecurity. That changed since the beginning of PrimeWater, for example. You can't procure anything without going through 13 documents on cybersecurity at Melbourne Water. So that's my first question is, all of that open source software, which incidentally I love and enjoy, is not even going to get through procurement or, our legal team, irrespective of whether it's a cloud service or not. So I'm quite skeptical about the operational endpoint, but I think there is a lot of value. It's just we're not capturing that value. I think the planning benefits, the policy benefits, for example, at Melbourne Water at the Western Treatment Plant, the development of a hydrologic model and the calibration of that model and the sanity checking of that model can leverage the remote sensing data, which is what we're doing. Temperature, surface water temperature is something we'd love to get because our water bodies vary. Even at Western Treatment Plant, there's a gradient. We don't have sensors everywhere. Do we expect to use this in an operational mode? Not anytime soon. So I guess my point is to try and be flexible in the benefits that you capture, because I think there are real benefits, and don't squeeze everything into this is going to be the weather service for a water quality model, which I know is the sales pitch from CSIRO, but utilities will see through that very quickly.
It was an interesting word choice when I saw that. And I did think there are certain expectations associated with that. And so thank you for your comments.
Thanks for that. It's always good to hear those kind of comments. And there's this real tension. I got a science background, of course, and then you talk to the communication people and the marketing people, and man, they turn things around, right? So we've been asked to say some things that maybe we wouldn't otherwise do. Certainly, the benefit of talking the language like weather service for water quality is that everyone understands what we're trying to do. Yeah. Yeah, so it's really, I think it's raised the profile of this issue nationally, actually. And so I agree with you. The
it's more of an aqua watch saying, I think, the weather service for water quality than necessarily, I can't really talk for PrimeWater, but that's more of an aqua watch thing than a PrimeWater thing necessarily. But the scope is certainly being developed now in partnership with people who are telling us what they need, right? So what we're actually promising at the moment is not that we will solve all the problems, but that we will be a good partner and work with whoever wants to work with us to try and make this something useful for the partners that we're working with. I agree, though. It's certainly, I think the application of something like this will vary very significantly between institutions and between places. And, you know, some of our partners like Hunter Water, I think have been really very well engaged, and others less so. But it is early days for this kind of a thing. But it's don't write us off just yet. You know, we'll yeah, sure.
I didn't mean to be a killjoy. I'm just bringing up some of the some of the issues just to bring it home a little more. So we're currently in the middle in Melbourne and I'm at Melbourne Water, so I'm very much aware of this. In the middle of a parliamentary inquiry about a certain flooding event that occurred in a certain suburb and led to people losing their homes. And in the relevance here is that there was a flood forecasting model, you know, with all sorts of sensors in the field. And the veracity and the functioning of that model and the arrangement between institutions is subject to a parliamentary inquiry, which could very well lead to significant implications, you know, for those who are affected and for those who might have partaken and support those services. So I just want to put that context there. When it comes to operations with large things at risk, then the delivery model is as critical as the technology service. And that is something I think that all of these enterprises, be it PrimeWater, AquaWatch, really need to understand and where they fit into the, you know, that world.
Yes, so that was a good comment, and it does remind me of what happened in Queensland with the group that is operationally mapping all the vegetation in Queensland on a very regular basis. They found illegal land clearing using satellite imagery. That became a court case, and there have now been multiple court cases. But the first court case they were involved in, the judge said to them, I have no reason not to believe you and your remote sensing images, but I want to see a full chain of custody analysis done. And that cost them half a year. They had to rigorously map all their processes, and every pixel, effectively, there was a chain of custody that had to be implemented so that it was clear that no manipulation of digital imagery could have taken place. That is when you become legal. Now, I'm actually involved as a counter expert in a dredging case using remote sensing, and all those issues are popping up again. But we did brainstorm about 15 years ago. It's when we end up in court, we know remote sensing will be taken seriously. So it's another way to look at it. How would you summarize that, to put this?
I think my comment is also about the value that those who are currently involved in these enterprises bring, because I'm involved in managing a large number of research groups, and to put it very simply, researchers generally don't make good business operators, right? And that's not where they add value. You know, it's innovation and it's prototyping. So, and I guess that's difficult because in the case of AquaWatch, there's a lot of money at stake. I'm very interested in the funding model, because if it's a subsidized model, then we'll be able to partake in it very easily and we'll support it. But if it's fee for service or largely cost recovery, then the price point is going to be critical for us. And we're also going to recognize that the entities involved are not businesses, they're research organizations. So that's why I'm bringing that up, because the question really, I think, is not just a technological one, it's what the existing research organisations, CSIRO, the EU equivalent, etc. How are they going to provide services that they on sell or whatever? With all of that model.
So over to Neil Sims from CSIRO, who's deputy lead of AquaWatch.
Thanks so much to you both. That's a really interesting question. Again, what we've seen in some countries, for example, is Chile, for example, is that you make these data services freely available and openly available, and then commercial organisations find a way to slot in there. And so, for the desalination industry, there are organisations now essentially converting this freely available information into the kind of formats that desalination operators need to see that in and selling that as a product. And I think it's the same for the aquaculture industry over there, multi-billion-dollar industries. CSIRO is an unusual entity to work with in many ways. Usually the way we do things is cooperatively. So we have a sort of a co-funding model where we say, you bring some money, we'll match it, sort of thing. And it's always a little bit rubbery around that. But we could do fee-for-service things if you really wanted us to as well. We were talking about the same thing with Apostolos, actually. The link between PrimeWater and AquaWatch is an interesting one too. So lots of opportunities. It can happen in many ways. The commercial end of this is something that's evolving now. The opportunities, I think, is something that's evolving now. But another sort of implication of the weather service for water quality thing is that most of our data is going to be free. Most of this is going to be free to nearly everyone, right? We have some great opportunities like with some high resolution data providers where we might say, if we reckon something's going to happen somewhere pretty soon, or there's a fish kill going on or something like that, you might have a commercial opportunity to just smash it with imagery, for example, right? So get very frequent, very high resolution imagery of particular things. And of course, we're talking about, Menindee Lakes type things there, right? Fish kills and etc. But the model, essentially what we're doing here is trying to, there's been no shortage of interest in the issue from everyone we talk to. Goes, water quality, really good idea. Nationally, globally, getting a lot of traction from everyone. And we're at that point now, I think, of needing to make a call, essentially because of the capacity that we've got in AquaWatch, capacity limitations, about exactly what we focus our initial energies on, and the sort of key points. You're asking great questions, and I don't know if I've even answered them very well, but it's evolving.
So before it goes to Janet, I want to ask if there are end users or stakeholders online, and then Janet can. Okay, go ahead, Janet.
So I just wanted to get Neil to clarify this, because I heard Alex Held say that CSIRO was not going to operationalize this. We're not in the business of operationalizing things. So, it will be passed on. So we're getting it to the point, and we'll have operational, the pilot sites, and they'll be tested and made good. And then we'll be looking for a commercial, well, not commercial, but an operationalizer partner to take on that one. Can you confirm that?
Confirmed. That's pretty much exactly right. So CSIRO, we're building this system of technologies and kind of hopefully a community of users that'll keep this going in perpetuity. The mission, the AquaWatch mission, really goes out. Our planning is out to about 2030, and we don't want to stop the system then. We want to have started something that continues. So there's a number of options for who delivers that operationally into the future.
So we're talking a lot about the Australian situation, and that's logical because we are in Australia. Let's remember that this is initiated by PrimeWater, and PrimeWater was way ahead of the game in 2019. It got established. They actually conceptualized this whole idea of, okay, we have to merge all these different methodologies and see if that becomes more powerful than each of the in situ data, earth observation data, and water quality modeling on their own. And we're also we are looking at ways that the PrimeWater Consortium and whoever in Australia wants to be part of the AquaWatch Consortium, because it should become a consortium, how they can all maybe work together, either in Australia or in Europe or in other parts of the world. So there's an incredible potential scope. I just want to explain one thing on the computing end, because computing for a long time has been a kind of a bottleneck, also because of the costs of the very high-end computing that you needed to manage these massive amounts of data. Where it's going now is that a lot of the remote sensing data is available in the open data cube, so it is accessible to everybody. You do need to process it, but the processing is now scaled up. In the case of AquaWatch on the Amazon Web Services, which means that whether you process 500, 5,000 or 500,000 images, it gets done in almost the same time, because the cloud just scales up to 10,000 or 20,000 or 30,000 clusters. So one bottleneck has disappeared from that point of view. And the costs of the computing, therefore, are now more honest. You pay per use. And so, yeah, okay, you might have to start paying a few dollars a day for the processing for your catchment area, but that would be the cost of computing. So that has now drastically reduced. So that's a major barrier that's gone. Now, does anybody have any other issues they can think of? I think there was another category that was put there, which is integration with regulatory frameworks. Who put that there? Because that is actually a very important point, probably. Was that somebody online or was it somebody in the room? Carrie Rouse. Okay, Karen Rouse. Karen, are you online? Karen? I can't see if you're online. I can't see the participants. Samuela, is Karen online? Karen Rouse?
I cannot find her. No, I think she logged off. Yeah, I cannot find her.
Here.
But if anyone has a comment on that, please feel free to.
Okay, so Karen
yourself.
isn't online. No, but
No.
the integration with regulatory frameworks is important. And then that whole legal aspect pops up again, which is how accurate does it need to be? And in what spatial temporal domain? Because the accuracy of an in situ measurement, for instance, is accurate for those few liters of water you're sampling, but is it representative of the entire water body? Remote sensing data in general per pixel is less accurate than an in situ measurement, but over the entire water body may be more accurate. And if you feed it into a water quality model, that may be the most accurate because it also has the three-dimensional aspect in it as well. Because that's also often also not realized that Earth observation does only look at the top few meters of a water body.
Arnold, I'll move into I want to just mention something. I am looking at the risks and I see mention to trust and the confidence in the tool. I want to ask the presenters if they have any comment on that.
So there's actually several trust issues. If you look carefully at the risks, they are formulated differently, but they end up being trust and reliability issues. Well, they're connected. Any comments on that? Nick?
I'll make one other comment, hopefully a little bit more positive. The way we're looking at this at the moment is sort of a function of the existing remote sensing platforms, if you like, Sentinel-3, Sentinel-2, the AquaWatch mission, and so on. But what we're all observing is this proliferation of platforms, kind of a democratization of the data access. And what PrimeWater's developed, and I guess AquaWatch will develop, and others, is the ability to ingest different data from different sources, constrain that data through the understanding of the underlying processes, so that physics-informed approach. And I think that is a highly valued development. So
Yes.
what I'm getting at here is that, our imagination is in a sense constrained by the existing platform, but what you've actually developed is the ability to take these different data sources, which are different ways of looking at water quality, and integrate that to value add. Now, what would be really good for the water industry is that if you could continue in that spirit and be able to ingest other types of data, for example, near map data or, planet data, particularly in the case of the water industry, smaller spatial scale and higher temporal resolution. So, return time is really important, and smaller spatial scale is really important for operational, but also for planning purposes too, because our assets are relatively small compared to the assets that satellite imagery has traditionally looked at. So I think you've got a very valuable commodity in that area if you're able to leverage that ability that you've created.
Yeah, so if I may summarize part of that, which is that, of course, as a water utility, you don't want to be involved in the complexity of what data, what format is it, how do you process it? You actually would just want the images or the trends. No. So there's a real opportunity there. And what about, okay, so for Earth observation data, that's clear. You think, the PrimeWater, let's say AquaWatch consortium, would be, if they could do all the data wrangling, then it would be a massive relief for all the utilities and water management authorities so that they don't have to do that. Sorry, yes.
I suppose you'd have to be selective about which platforms you bought into this munging of data, because you need some ground truthing and you don't want to end up in chaos. But that's another thing we'd be relying on you to do, which is know which data sources to bring in, not be particularly jealous about a particular data source or favor a particular data source. Just bring them in according to the merit of the situation. Like some of them might be provided commercially, like planet data, for example. Some of it might be the open data, like Sentinel-2. Some of it might be like near map. Being able to combine that with the sensing data that we generate in situ to get that value add, I think that could be really, it's something that we wouldn't have the time or the expertise to do, and it could add a lot of value.
Okay, that's a great point. Thank you. So going back to extreme events, because you spoke about extreme events, there's an example, and I think Janet and Neil know more about it, but I just saw the results recently that there was a fish kill recently in the Menindee area again. And the river where the fish kill took place is quite narrow. It's overgrown. There's a tree canopy, but I think Neil, Sarah was able to order planet data. Do you want to explain what you did? Because that was actually quite a nice example of this. So Neil, can you?
Yes. So, you're exactly right. We know that the freely available data sets that are easy for us to use don't cover all of the needs of the end users, and something like the Darling around Menindee is a pretty narrow channel actually, and so what we did basically was we'd heard about the fish kill. CSIRO was compiling a response essentially to that, a scientific response. And I just contacted the guys at Planet, who we've been talking about for AquaWatch anyway, and said, what have you got over Menindee? And they came back with months of daily high resolution data within 12 hours that we could use, right? They were very, very generous. Thereafter, a commercial arrangement, right? I totally get that. And that's probably a way to do it. What we're finding with some other government institutions, essentially they pay a fee to Planet, and Planet helps them out when they need it, sort of thing. So you don't pay per image. They make that available, that imagery available publicly, and it's already covered by some bigger arrangement, and maybe something like that can happen for AquaWatch. One of where we are, we're a science organisation, CSIRO, and the science in this, led by Arnold and Janet and other really smart people for a long time, has been that retrieval, the retrieval of water quality parameters from a measurement from a satellite, right? A measurement of the colour of the water, essentially, one way or another. That's really the part that's the underpinning technology that we're using. And so some of these satellites, some of the sensors, for example, the Planet ones, are great for a high resolution picture, but don't let us analyze some of those contents of the water because they don't have the right spectral characteristics, right? So, but as an ecosystem of imagery, we have this high resolution stuff. You can get a good look at it. We've got, you know, hyperspectral stuff that comes over not very frequently. We've got multispectral stuff that's got big pixels but comes over pretty frequently. We've got this stuff with a really long archive of data, and together they sort of give you an impression of the history and the likelihood and these things. I think that's the way to think about it.
I know what am I hearing is got relevance to information ready data and analysis ready data. So utility may want to use some data set for a particular angle or particular use. They may not use a generalized information that we are talking about, daily weather quality information. And there must be caveat, and we'll be using caveat that this is based on this. Yes. And it might not be the right one, sort of thing. So I was thinking, if you've been talking about information and analysis ready data, more light onto that.
Yes. So, okay, I was asked to. So there are 3 categories of data you can get from Earth observation currently. And I'll skip the raw data. One is analysis ready data, which is atmospherically corrected, geo-corrected, sunglint corrected, if it's terrain corrected, etc. And so that's water leaving reflectance or water leaving radiance. And people can apply their own algorithms to it, but they don't have to wrangle the data to do all those corrections that's been done. The next level is interpretation ready data. Interpretation ready data is, for instance, chlorophyll maps or cyanophycocyanine maps or total suspended matter maps. So they've already been translated to a water quality variable. Those are interpretation ready data, but there seems to be demand for decision ready data, which is that you say that, for instance, we want to know if this lake system is becoming less eutrophic because we've taken quite a lot of measures in the catchment to reduce nutrients going into the lake. And we want to see if our management interventions actually have resulted in a reduction in, for instance, total suspended matter. So that would be decision ready data. And in an end user survey we did for AquaWatch 2 years ago now, where there were 90 end users with a very good distribution across all the types of end users. They lost my thought. Where was I? Yes. So no, there was another track I was going on. Okay, lost my track. It will come back to me. Yeah. It is, but okay. So now I'm going back to the end user. So we found in those end users, because now I know what was complicated, is we found that of those 90 end users, there were about 10 to 15 who said, just give me the analysis ready data. Because we can apply our own algorithms, we're in control of that. Then there was another group. There was quite a large group who said, no, we want interpretation ready data because we are very comfortable with our GIS systems, work really well. We can integrate it with all our own data. And then we are happy to make the product, the information products we need ourselves. But there was actually quite a category of people said, and especially local councils in Australia, who have got large areas to deal with, but with a very small population. Many local council areas just have 10,000 or 15,000 ratepayers, but they've got the size of half of Belgium to manage. And they say, we just don't have the capacity. We just want decision-ready data. Just tell us what our problems are and give us the solutions and the money as well. But no, sorry. So that was the quite interesting out of that end user survey, that there is not one type of data that fits all. You've got levels of, let's say, capacity and capability in end users. So that poses a problem, because it also means that if you do want to provide a service, you have to offer all the three those categories to please all the different levels of capabilities in your end users. So that is actually quite a complexity that is often not thought about. I want to know, is there anybody online, because the discussion has been here, is there anybody online who would like to say something? If not, there is something I have picked up in multiple discussions over the last few days, which is the role of citizen science. Citizen science, for instance, by mobile phone apps, has not been discussed here. It's not in, I don't think it's in any of the opportunities, barriers, benefits, and risks. Yet, a lot of people have been privately discussing that the role of citizen science could actually be underappreciated at the moment, and that we may need to spend more time and effort on it. Would anybody like to comment on that? Anybody online? Online first? Oh, come on. Neil, would you like to comment?
I'll give it to someone who knows more about it, actually.
Okay, Janet.
Okay, so as part of the AquaWatch, we are in discussions about integrating a water quality app into the program. And we think it's the water quality approach, looking at watercolor, is complementary. It's different, but it's complementary to the AquaWatch products that will be output. And in the same way, it could be complementary to the products that are produced through the PrimeWater project. So these efforts are underway. There's a range of different water quality apps that are out there. The one that we've been working with in CSIRO has been the Ion Water app, which we've been using at the Melbourne wastewater treatment plant quite often. And this gives us an opportunity to not only engage with the community in terms of the visualization of the PrimeWater or AquaWatch products, but actually give them an opportunity to see their data integrated into these products and have a two-way exchange of information. So that's where we're heading with.
So that's a real opportunity, actually. Yeah, I think it's an opportunity we should capture here, because it has popped up in a lot of discussions and it's not showing up here. And I'm like, okay, so I'm interested in two things. Why doesn't it show up? And why is it discussed so often? So that's an interesting, but Apostolis was first and then Neil.
I just wanted to follow up a little bit, the discussion about the data and all these layers of data that are there or could be there. And I think the possibilities there are huge in terms of making people's life easier, in terms providing the necessary information base the way they want it. And for example, science can play their significant role trying to figure out how actually to work with those data, because it's not easy. If you start working with it, I mean, even if you have data available, it's not easy to work with the data, particularly if you want to work together with to integrate all those data in concepts. And it becomes even more challenging when citizen science data start influxing into the equation. So there, for example, that would be a great area that science can support this field by trying to make all those different types of data integrate, fuse, produce, reanalysis data, fill the gaps in a reliable way that then can meet much more easier the expectations or the planning purposes of end users. Imagine, for example, a lake that now might have scattered data, 10 years, for 10 years, 15 years, measurements of in situ data in 3-4 points around the lake. How many years? 10 years of satellite images. But imagine you can provide reanalysis data in each one of the cells of the grid of that lake 30 years ago, by combining this data, by combining modeling, by combining citizen science, by combining a lot of these diverse data sets. And I think this is the great challenge, both to scientific community, but also to the users community. How you actually to get access to strong reanalysis data that actually bring together all the benefits of individual data sets into a unique, strong data product. That'd be one nice challenge for the future in PrimeWater, but also AquaWatch as well.
Arnold, we have a raised hand.
Okay, Gerard, please, go ahead. Unmute
All right.
yourself.
Yes, I've unmuted myself, so you should be able to hear me.
Yeah, we can hear you.
Good. I work for Water New South Wales in Australia, of course. And yes, I just wanted to say that we already use citizen science, I suppose, as many of the people in our position use, organization in our position use. For instance, when managing blue-green algae, so we've got people that can come in and give us a call or send us an email. We've got 4 RAC coordinators in New South Wales, so that information can come into us as information like photographs or just reports about what people have seen, and then we can follow up with that. The issue that we have with citizen science is very often is that how reliable is it? That's a question. So what we do in that sense is that we go and verify what we've heard about and what we've seen by sending our own crew out or verifying by with the satellite images that we receive. Basically, that's how we handle that part of it. So if that's any of any use to you.
Thank you. Thank you. So that's okay. That's the other way around, that it can work as well. That the citizens alert you to something, and then you use the remote sensing data to, amongst others, remote sensing data to check what's going on. Is that correct?
Yes, that's correct.
Yes.
And yes, what
Okay.
you propose is just a step further. So
It would be a step further. I think the citizen science apps could go down the path that they do only function in a certain way, so that whoever is the person operating it has to follow a certain protocol, which then gives you some reliability of the data that you're capturing, which is the Eye on Water app actually has some of that in it nowadays, and the Cyano Lakes app as well. Nick. Thank you, Garrett.
Yeah, I wanted to make 2 points actually. I guess just going back to the previous discussion, what I see in the PrimeWater and this group, and particularly with Janet and others, is a real deep knowledge around water quality and what affects water quality. And I'm sure the future will be physics-informed machine learning, not just machine learning. And so you've really got something to sell there in terms of the future algorithms and their development. Citizen science for us, my comments are restricted to Melbourne Water, and Melbourne Water has 2 functions that are a little unusual in the water industry in Australia. One is a waterway manager function. And so we are actually formally delegated as the waterway manager to declare a water body as not suitable for recreation. So we are very enticed by citizen science in the possibility of giving us greater coverage of the many constructed water bodies around Melbourne, like there are literally hundreds of them, in much the same way as the person from New South Wales was describing. But I think we would look at it a little bit like, you know, when you listen to the radio and there's that 1 minute delay in case somebody swears on live, we'd want to have that 1 minute delay. And I think that would be really important for the deliverer of the service as well, because otherwise you become the de facto EPA or the de facto formal authority which declares a water body as not being fit for purpose or whatever. Yeah. So I think in short, I think it could be really valuable if it was treated.
Curation is important.
Yeah, if it was just the way it's handled would be really important. Yeah.
So some form of curation is essential. I do have one point to make. You're talking about ground truth, all of you. Aren't they just ground measurements with their errors associated with it? As is Earth observation. It's a measurement associated with errors. Because the term ground truth is misleading. to my field because it's not the truth. It's also a measurement with strengths and weaknesses. So for instance, if you rely on fluorescence measurements in water and you want to translate it to chlorophyll, can you vouch for that all the time? You know, that's a big question. So the same issues apply, but I'll just avoid ground truth and just say they're both measurements. Let's make the most of them. That's just my personal little point. Somebody else wanted to, did you want to? We're going towards the end of this session, by the way.
Yeah, I was just saying with the citizen science, getting input from the customers, general public, like we're integrating an application called Snap Send Solve, like for our field teams, but it's already out there where people can see a broken footpath or a street light hanging or things. We're already like, that's already kind of out there. And that was just a comment to say that we're already starting to pull some of that in anyway, like,
okay,
and looking to expand that out. So could, yeah, just want to add that.
Jen, I think you're going to be the last because we're at time.
I was interested in the New South Wales example. I'm just a plug for a topic that I'm the editor for in Frontiers. It's environmental citizen studies in freshwater science. So we're compiling a whole range of case studies globally using citizen science data integrated into freshwater science.
Okay, great initiative. Now, I think we've reached time. So I'd like to thank everybody online, everybody in the room. I think the opportunities, barriers, benefits, risks, and other categories now have a nicer distribution. But that's, I actually do see some duplication. Quite a lot of these fields could be merged and become a little bit more comprehensive because I was in a very quick look. You can see that some are addressing the same topic in a different way. So I think, you know, we have to go through this and then summarize it. But I think there are some amazingly good contributions. It's been very honest. Everybody's been honest. Everybody's been very civil, which is very nice as well. So I'd like to thank everybody online and everybody here. And I think this is a great result because I think these kind of interactions will help us mature this area and make it more useful because we're getting honest feedback. So highly appreciated.
Well, this is the part of vote of thanks. And we requested Aras, who actually opened up the session, to do the vote of thanks, and looks like he's busy somewhere. So I don't want to delay this session anymore, and I take this opportunity to thank sincerely all the speakers and also those who attended from several parts of Australia as well as from overseas, particularly Apostolis. I know that some of your colleagues got up early in the morning, and Samuela told me that the time she started, it was 2:30 a.m. in the morning in UK. So she deserves a big applause, as well as you know, Evangelos, also from Greece, got up very early. So a very big John, your hands, please. Very big appreciation to you guys, and also I would like to take this opportunity to thank a local organizer, particularly Aras, Kemi, who worked very closely with myself and Samuela over there to organize this session. So thank to you, Aras, and Kemi, for organizing such a interactive and informative session. Do you want to say something?
Just small information. We intend, I mean, it's great that we have collected all this feedback. It's very important for us. And we intend to consolidate the messages out of this communication and then come back with a short summary note about what happened here today. It was very, very valuable. and we hope we have other chances like that in the future to collect more. I mean, to engage in this discussion with you guys and wider. So just that's what I wanted to say. But we'll come back with a summary report about today's conclusions. So thank you from my side and also the team, PrimeWater team.
Oh, we lost you, but for everyone both online and in person, PrimeWater is running a survey on user preference for Earth observation services. I put the link in the chat, so please do take some time to fill out this survey because it really helps further activities of the project.
Sorry for that, for popping in, but I think this is a very interesting angle that we've tried to have in PrimeWater, and I really would like you to just spend 10 minutes of your time to fill in this questionnaire, because it's a completely different approach in trying to quantify how people make decisions against innovation, against remote sensing or these tools. So this is an experiment that has been designed by people that work with these techniques, trying to elicit how people actually make decisions. So we have prepared this questionnaire. Actually, it's a scientific experiment that tries to quantify the weighting among different decision options. So it would be very useful if you guys just find 10 minutes of your time and just give us a feedback. It will be really valuable. And again, this will lead to a consolidation report. We have run a first round of analysis of those data, and they're giving very, very nice insights about how, at least those people that reacted. Think about that. So it would be great to have a larger number of responses.
So thank you very much. And, we would like to conclude our session today. And those who have joined from other side of this desk, thank you again very much, and goodbye.